Hello, everybody. Welcome to lecture. We are going to get the exams back on Friday. I'm working on grading them right now, and I'm over halfway done. And so far, things are looking okay. They're looking fine. Yeah, No, it's not. It's hard to tell because you just see like one section, like the radical section, the class did really well on it, and then there were some aspects of conjugation that were a little weaker than I was hoping. But overall, so far it looks fine. I mean, some people are doing really good. It's hard to tell. Before it's all done, you can't really weigh in on it. So, yep, I'll have that back for you in class on Friday. I'll probably finish grading them tomorrow. So what we're going to do in the meantime then is talk about some new stuff. So we're into chapter 16 now, which is reactions of aromatic compounds. This is all about how benzene and its related compounds react. So there is one big reaction that we're going to be looking at in this chapter, and it's called electrophilic aromatic substitution. Electrophilic aromatic substitution. And the overall reaction looks like this. If you take a benzene ring, like I'll just show benzene as the first example of this class, but it can be other things too. The benzene ring can certainly have substituents on it, but let's just look at the simplest possible scenario where it's just plain benzene with H's all around the ring. The way that the reaction goes is if you put this in with an electrophile, and I'll label that as E+, and so I'll say right here that this represents an electrophile, which is a species that's electron poor. It's usually got a plus charge on it, and it's always hungry for electrons. So it is attracted to the aromatic ring because the aromatic ring has a lot of electron density in its pi cloud. That donut, those two donuts of electron density above and below the plane of the atoms, those are good targets for molecules that have a positive charge, especially a really strong positive charge. And so when this electrophilic aromatic substitution reaction happens, what comes out of this is a benzene ring that has an E substituted in place of one of the H's. So it essentially is the electrophile E substituting for a hydrogen somewhere on the benzene ring. And then the other product would be proton. So that's electrophilic aromatic substitution, and essentially it's just one of the hydrogens swapping positions with the E+. That's the overall result. The mechanism's a little bit more involved than that, and we're going to talk about the mechanism. And understanding mechanisms is really important because it'll allow you to understand what's going on in the reaction, and then you can start predicting what products will be based on some resonance trends. And the E is not a specific reagent, it's like a generic electrophile, but we're going to be talking about specific electrophiles very soon. But before we get to that, let's talk about the mechanism, like how this works. Step by step, what bonds form, what bonds break, what order does it happen in, what are the energies of the intermediates, if there are intermediates, transition states, energy changes, all of that stuff that is important in understanding a mechanism of reaction. So there are usually 3 steps in all these processes. So step 1 is the active electrophile forms. That would be that E+ species. These electrophiles, these E+ species that we're going to learn about, are so reactive that they're not the kind of things you can put in a bottle and store on a shelf. Instead, what you do is you usually mix reagents together that make a really reactive E+ that is got a short lifespan, and so you have to make it and then it gets used right away. So the first step in the mechanism is usually generating that E+, and we're going to talk about that for several different reaction types. Then, second step is the electrons in the pi system of the aromatic ring make a bond to E+. And that's going to generate, generating a non-aromatic intermediate. And I'll just put in parentheses here, resonance stabilized. Because it's resonance stabilized, but it doesn't have aromatic character anymore. Intermediate. And then the third step, the last step, is that a weak base deprotonates the non-aromatic intermediate to restore aromaticity. So you start with an aromatic molecule, you end with a substituted aromatic molecule, but in the middle it goes through a stage where it becomes non-aromatic, much higher in energy. So there's this series of changes that the molecules go through as they progress through this mechanism of electrophilic aromatic substitution. So I'm going to show you steps 2 and 3 in a generic sense. We're just going to start with a generic E+. I'll show you the mechanism, and then we're going to talk about a lot of specific reactions where the substituent is like a real substituent. You could make a benzene ring with like a group like a chlorine or a bromine on the ring, or put a nitro group on the ring. There's a bunch of different reactions that we'll talk about. So let's talk about mechanism in a general sense. And we'll think about all of these steps as we go along. What happens in step 2? What's the non-aromatic intermediate? How does it get deprotonated? All that sort of stuff. Okay, so first step is make E+, the active electrophile. The second step is that the electrophile gets attacked by the ring. So the electrons in this aromatic ring are attracted to E+, and so E+ is going to do a reaction here with these. So I'm going to draw hydrogens out on this ring just for reference. You're not always going to see all the hydrogens drawn in because these structures are a lot of times going to be skeletal structures, but let's just look at it right now with the hydrogens all drawn out. Take a pair of electrons out of the ring, like start an arrow at one of the double bonds in the ring, and it doesn't matter which one for benzene because they're all the same, but I'll just start right here, and I'm going to take an arrow and show it pointing to E+. And what that means is the electrons in this pi bond, a pair of electrons, are going to reach out and make a bond to E+, and then it's going to get connected to either one of these two carbons. If it's closer to this carbon like it is, it's going to get a new bond between that carbon and the E+, and we're going to leave that carbon with a positive charge. So the intermediate that we're going to get here looks like this. We're going to have, we just added an E to the ring, but we've got a plus charge on that carbon because it used to have a double bond and now it doesn't. We took some of its electrons away to make a bond with the E+. So this is the non-aromatic intermediate. and it's resonance stabilized. You can draw some resonance structures for this, which actually helps explain why it's somewhat easy to form. So I'm going to draw that. I'm going to draw the resonance structures. Next door, there's a double bond that I can take a pair of electrons from and just shift them over. So that shifting of electrons is going to share them differently, and now we're going to move the positive charge from here over to here. So it shifts the location of the positive charge, which helps to stabilize the intermediate because the positive charge isn't stuck in one spot, but rather it's delocalized across multiple atoms in the ring. Okay, there's one resonance structure, two resonance structures, I guess I would say, and then there's another one. I can draw yet another resonance structure where if I just push the positive charge further along the ring, I take this other double bond and push those electrons over that way. I can make a structure here, a resonance structure, where the positive charge is delocalized onto yet another position. So the positive charge is shared across 3 different atoms in this benzene non-aromatic intermediate. So I'm going to just say that, and I'll put brackets around them to indicate that these are resonance structures of each other. This is the non-aromatic intermediate. All of these resonance structures collectively are describing the non-aromatic intermediate in this electrophilic aromatic substitution reaction. All right, that is step 2. That's electrophile gets attacked by the ring electrons to form this non-aromatic intermediate. Now the last thing that happens, the third step, is that a weak base comes by and plucks a proton off to restore aromaticity. So we're going to talk about that, and what I will do is show it from, you could show it from either one of these, any of these resonance structures, but I'm going to pick this one because we can just kind of flow this mechanism further that way to continue on with it. So I'm going to adjust the view here so we can see this last resonance structure and what happens in step 3. The weak base is sometimes a very weak base. It kind of depends on whatever you brought in as the counter ion for E+. So the E+ electrophile is positively charged. There's something negative that was associated with it. Usually it's that counter ion, or oftentimes it's that counter ion that acts as the base. But since we're doing a generic kind of reaction here, I'm just going to say base, and I'll draw a pair of electrons on it. And what happens is it's the sp3 hybridized carbon, that's the one that gets deprotonated by the base. The reason is that's the point where it's non-aromatic. So if you pluck off that H, you can share the electrons into the ring and you can restore aromaticity by restoring conjugation. This ring is not conjugated anymore. It's not fully conjugated because there's this sp3 hybridized break in conjugation. So what the base likes to do is to grab the proton out of that position, and then those electrons can be shared into the ring, and then you get this species that now once again has a full conjugated ring, and we're back to aromatic ring again. And so the energy now is a lot lower than it was with the intermediate. The base has picked up a proton, so it's now the conjugate acid of whatever base you started with. And that is the reaction, the mechanism. And what you'll see in this chapter is there's lots of different examples with different E+, but it's the same mechanism every single time. Different E+, slightly different base, but the mechanism is going to be consistent. So even though we're going to look at a lot of different reactions, they're really not that different. So it's worth kind of getting used to this mechanism and getting comfortable with it. So let's just give you a little preview of what is coming. But maybe first, though, I should give you an energy level diagram of what's going on here. Because we've got these two steps. It's a two-step process. Once you get the electrophile, that's the first step. But then steps 2 and 3, if I graph those on an energy level diagram, you'll probably have some deja vu. So energy's on the y-axis and it goes up. Things that are higher up are less stable. Things that are lower down are more stable. And this x-axis is reaction coordinate. That means just the passage of time as the reaction progresses from starting materials to intermediate to product. You're going to go from left to right. It's like watching a movie of the reaction. You could like start at the beginning and then pan through to the end, and you can see the intermediate in the middle. So let's just draw a line here to represent the energy of the starting materials. This would be the benzene ring and the E+, the two reactants. Then I'm going to draw a line right here to represent the energy of the non-aromatic intermediate. And I'll just draw one resonance structure of it because it's kind of challenging to draw all of them. There's not enough space to really do it well. So that line right there represents the energy of that species. And then down here at the bottom, I'm going to show the energy of the final product. And there is also a base that's involved in this too. I'm not going to show the base in the energy level diagram, even though it's an important reactant. But essentially, these are the and there's got to be an H+ to balance it. So we've got reactant, intermediate, and product, and there are a couple of transitions that happen here as it goes through on from reactants to intermediate to product. So you'll notice that the reactant, the intermediate, is really high in energy. It's a carbocation. It's a resonance stabilized carbocation, but it's a carbocation. And this graph, if it looks familiar, it's the same graph that we had when we were studying SN1 reactions in organic 1 and E1 reactions in organic 1. It was a two-step process. The first step was form the carbocation, and then the second step was carbocation reacts. Substitution reaction, it got substituted. Elimination reactions, it got deprotonated. This is really really similar to an elimination, E1 elimination mechanism, really, in its energy level diagram. And because that first step is the highest in activation energy, you look at the height of the hump going from reactants to intermediate. This E sub A1, the activation energy of the first step, is a lot bigger than the E sub A2, which is the activation energy of the second step. So the first step is the rate limiting step. Forming that non-aromatic intermediate is hard, and it's slow. And so once you get this, though, the second step is really pretty fast. Okay. Then you can also, just like with all the other energy level diagrams, you can look at the energy difference between reactants and products, and you can see there's a delta G value that's associated with it. So that tells you whether reactants or products are favored and by how much. The fact that the product I'm showing here lower than in energy than the starting materials means that this is a reaction that's going to favor products. It's going to have an equilibrium constant that's greater than 1. So, so you can learn a lot from these diagrams, but basically it's describing in energy terms and structure terms what's happening in steps 1 or 2. After you form the active electrophile, the next step is form the intermediate, and then the last step is deprotonate the intermediate. So that's an introduction to electrophilic aromatic substitution, and that mechanism we're going to see over and over again. But do you have any questions about the energy level diagram or the mechanism or the non-aromatic intermediate? Any of that stuff? Yeah, question. So would delta G be negative then overall? Yes, for this process, the way I've drawn it, delta G is negative, and you could say products are favored. And if you knew delta G, you could predict by how much. So there's this 6 kilojoules per mole as a factor of 10. in the equilibrium constant sort of rule of thumb that I gave you last semester, I'm not going to ask you about that this semester, but just pointing out that, if you knew delta G, you could predict how much more favored the product would be in this reaction, for example. So, all right, let's look at some specific reactions. So here's a brief outline of the kinds of reactions we're going to look at in this chapter. At least electrophilic aromatic substitution reactions. These are the ones that you're gonna see first. Then later on, we're gonna look at some reactions where you can manipulate some benzene side chains, and that gives you a little bit more ability to build molecules that have a little bit more complicated structures. But first of all, we're gonna look at some electrophilic aromatic substitution examples. Electrophilic aromatic substitution reactions. This is where we're headed. We are going to do halogenation, and I'll show all of these with the benzene ring just as a starting point. So we're going to see that if you put this in with X2, where X2 is either chlorine or bromine, and I'll put that down here, I'll put that, I'll make a note of that over here. You can make a halogenated benzene. This is called halogenation. And I'll say here X is equal to either chlorine or bromine. Fluorine and iodine don't work very well, so we're not going to look at those. Also, we're going to look at reactions to put a nitro group on the ring. So nitro is a functional group that we introduced the chapter where we started talking about benzene nomenclature. Before I move on, though, I should say here that there's going to be another thing that you need in the halogenation reaction, and that's an iron trihalide catalyst. This reaction uses a sulfuric acid catalyst, H2SO4. And it produces nitrobenzene plus water. And I think what else? Anyway, water is the other product. This is called nitration. Puts a nitro group on the ring. Then there's another one called sulfonation, which involves benzene ring getting put in with SO3, H2SO4. It's a really strong acid catalyst to generate something called sulfonic acids. So this is a sulfonic acid functional group. And this is called sulfonation. All right, those are groups that are not carbon groups. So, but some diversity, halogen, nitro, sulfonic acid. Now I'm going to look at and just tell you briefly what kinds of reactions we're going to look at that are about making carbon-carbon bonds to the ring. And these are called Friedel-Crafts reactions. And so if you're in the lab course, we did one of these yesterday. We did a Friedel-Crafts acylation. So that's one of two types of Friedel-Crafts reactions that we're going to look at in this chapter. So if you go in with a benzene ring or a related compound and you put in an alkyl chloride, and you use aluminum chloride as an Lewis acid catalyst. This reaction puts an R group on the ring, an alkyl group. So that's why it's called alkylation, and the other product is HCl. And since it's got a name associated with it, and some reactions do, we're going to learn that. We're going to talk about it. It's Friedel-Crafts. Alkylation. So Friedel and Crafts were the two chemists that popularized this, so their name is attached to it. And then one other reaction is another version of Friedel-Crafts, but this is Friedel-Crafts acylation. So instead of an alkyl group, we're going to put on an acyl group. And it's going to be aluminum chloride or other catalyst. As far as the textbook goes, in all the examples we're going to look at in lecture, X is going to be equal to chlorine, and aluminum chloride will be the catalyst, but you can do it with other acyl species too. Like in lab, we used the X group was an O carbonyl. It was just a different leaving group. And the other catalyst was a really strong acid, polymer-bound sulfonic acid. But the result in both of those cases is that you put on an acyl group on the ring, which is a ketone. And HCl. So Friedel-Crafts, instead of writing it out again, I'm just going to say FC, and down here I'm going to say this reaction is called Friedel-Crafts acylation. And so we're going to look at these 5 reactions as being kind of like the key methods for us to put things onto aromatic rings. And a big focus of this chapter is going to be, how do you manipulate matter to sculpt a benzene ring that's got things on it, and not just like in random places, but specifically in spots where you want them to go. So how do you manipulate matter at a molecular level and controlled construction of molecules, basically synthesis? That's one of the themes of this chapter too. Any questions so far about the 5 reactions we're going to look at? All right, well, let's get started with the Friedel-Crafts, or not the Friedel-Crafts, the halogenation reaction. Step 1 in halogenation is you form the active electrophile. So we're looking at active electrophile formation in this halogenation reaction is the first step. So the way it works is that you put your halogen in, which is either chlorine or bromine. So here's molecular chlorine. It's got 2 chlorines, and it's got lone pairs on each of these chlorines. And then there's an FeCl3 that's there as well. So the iron is, has a real strong partial positive charge because it has these 3 chlorines attached to it. And so it really wants to accept some electron density, and these lone pairs are good at providing it. So what happens in this first step, or in this active electrophile formation, is a pair of electrons on one of the chlorines goes and makes a bond to iron. And then that gives an active electrophile that looks like this. It's got the chlorine molecule now bonded to the iron. And I'll draw in all the lone pairs here on the chlorines that came from the chlorine molecule. And that one has a formal plus charge, so it's really very electron poor. And then the iron has developed a formal minus charge. And all these other chlorines have 3 lone pairs as well, but they're not the focus of what's interesting about this molecule. It's this over here. The way to think about this thing is to think of this whole part of it that I'm lassoing out here. Maybe I'll use a different colored chalk. To make it stand out. Think of this as a super leaving group. You know, chlorine by itself as chloride is a good leaving group. We learned about that last semester in organic. But when you hook an electron poor iron to it, it becomes a super good leaving group. Normal chlorine leaves as Cl-, which is already a weak base, but this species leaves as neutral chloride attached to an iron, and that's an even weaker base. So it's a really, really good leaving group is what I'm saying. And it's not that the positive charge exclusively resides on the chlorine. That chlorine has a formal negative positive charge, but this chlorine over here has some partial positive charge as well. So what we're going to see in the next step is that the electron cloud in the benzene ring attacks that chlorine, and then this functions as a leaving group. So let's take a look at that in this next step, unless there are questions. But this is the active electrophile in the electrophilic aromatic substitution reaction involving chlorine or bromine. It's you just have to hook the chlorine or the bromine to the iron. All right. So then step 2, pi electrons of the ring attack. Pi electrons of ring attack the electrophile. So what you want to do is draw your benzene ring. I'm going to draw this up just a little higher, so I'll have a little bit more room underneath it to draw step 3. So I'm just going to go up a little higher here. Here's the active electrophile that we just drew over in that previous step. I'm not drawing the electron pairs in here, but I could. I'll put them in one more time just for clarity. And then remember, this is a good leaving group. So start an arrow at one of the bonds, double bonds in the aromatic ring, and show it going to attack the end chlorine. And then this chlorine-chlorine bond breaks, and those electrons go to the chlorine that's partially or fully positive, that has the formal positive charge. So when that happens, you get this species, which now has a new chlorine attached to it right here, and there's a positive charge on the ring. And there's a counter ion that's here, which is the iron that has those 3 chlorines attached, and it just got a new chlorine attached to it and a formal minus charge. So that's the non-aromatic intermediate. It's resonance stabilized. I could draw 2 additional resonance structures of that molecule to show how it's stable, more stable than a typical carbocation. But that's this step 2. That's how the electrophile gets attached to the ring. And then the last step is what happens next is that weak base deprotonates the intermediate. So this is step 3. Weak base deprotonates, takes a proton off that intermediate. So I'm just going to take these structures and recopy them down here. I could run a scheme just down this way, but I just feel like redrawing these for clarity. So we have our non-aromatic intermediate that now has a chlorine attached. And its counterion is this iron that's got 4 chlorines attached to it and has a formal minus charge. This functions as the weak base. And the way it works is that one of the bonds between a chlorine and the iron functions as the base. I'll use this one since I drew that bond in, but if you start an arrow at the electron pair between chlorine and iron, you can show it going to that H to grab it. So effectively what you're saying is this chlorine is going to leave the iron, take that pair of electrons with it, grab that proton, and then the electrons in the carbon-hydrogen bond, they go into the ring. And that movement of electrons gives you the final product, which is an aromatic species. So aromaticity has been restored. And you get your HCl coproduct, and then you also get the catalyst back, FeCl3. It reforms and it can react additional times and catalyze another round of this reaction mechanism. So that's the final product right there. It's got a chlorine substituted in place of where one of the H's was. And that H that was originally there is part of this HCl molecule. So that's chlorination. Bromination is exact same mechanism, just with bromines in place of chlorines. So the thing that people usually have trouble with is the active electrophile. So that's one, it's a good thing to practice, is what happens when iron trihalide is mixed in with halogen XX bonded, chlorine or bromine molecule. Okay. Questions on this one? All right, now we can go on and talk about nitration. So nitration is number 2 in the list that I put up on the board. So nitration involves putting a nitro group on the ring. So what I will do is kind of follow the same format over here for explaining this mechanism. I'll start by just reminding you what the overall reaction is all about. So you start with an aromatic ring. And what gets mixed in with the ring is nitric acid and sulfuric acid. This is usually the way it's done. And what comes out of this, it's not a balanced equation that I'm writing here, but this is the product of interest. This is nitrated benzene. So step 1 is active electrophile formation. And it's interesting for nitration. Active electrophile forms. So it's kind of a crazy situation when you mix nitric and sulfuric acids together, because these are both very strong acids. So you have this like really intense, strong acid cocktail that you're going to be tossing this aromatic ring into. So we got to figure out what these do with each other. It's like 2 strong acids. What happens? Well, one of them is going to protonate the other. It's kind of like a cage match between acids. Okay, which one's going to win? Which one's going to protonate the other one? Which one's stronger? It's really what it comes down to. So here are the two acids. There is sulfuric acid, which has this structure. And then there's nitric acid, which has this structure. Both very powerful acids, but one of them is stronger than the other. I'm going to draw in all the electron pairs on nitric acid because they're all going to be important to think about. Okay, who's betting on nitric acid to win the battle? Nobody? Oh, how about sulfuric acid? Oh, lots of people. Yeah, sulfuric acid wins. Sulfuric acid is a stronger acid than nitric acid. So crazy as it seems, you take a strong acid, if you put an even stronger acid in, it'll get protonated. And this nitric acid has lone pairs on all of the oxygens that could get that proton. So any one of these oxygen lone pairs could theoretically grab a proton off sulfuric acid. But there's one that leads to a productive reaction, and that's this one. If this one acts as the base and grabs a proton off of sulfuric acid, what you get is a species that's set up to lose water. This was something we talked about a lot last semester in Organic 1, is like if you wanted to make an OH group into a good leaving group, put a proton on it. That makes it into water. And water is a really weak base, and it can leave really easily. It's a good leaving group. So that's exactly what we did here with this molecule. It's a protonated nitric acid. The rest of this molecule, this HSO4 minus, is still there. I'll put it down here. I'll say HSO4 minus is the counterion to this thing. But then what happens is this water ends up functioning like a leaving group. So I'm just gonna lasso it out here and say good leaving group, just like it was last semester, because it's a weak base. And it gets a little help from this O minus. So if you start an arrow at one of the lone pairs on the negatively charged oxygen, give it a push to share it between oxygen and nitrogen, and then this electron pair in the nitrogen-oxygen bond, give that a push out onto the oxygen of the water, and you get the following things. You get water as a product. That's not the interesting product, though. The interesting product is this species that's got a nitrogen double bonded to two oxygens and a formal plus charge on the nitrogen. And this is the active electrophile. This is called nitronium ion. Nitronium ion. It has a counter ion of hydrogen sulfate, which isn't really going to be all that important, but this is the species. That's the thing you really want to think about, because that's what the ring is going to be really attracted to. This is a intensely positively charged nitrogen, and the ring electrons are going to just go for it. So we're going to see that in the next steps. So in step 2, I don't even have to erase this little header that I've got here because it's the same. The pi electrons of the ring attack the electrophile. I just have to replace the electrophile here with nitronium instead of that halogen that had the iron stuck to it. So I'll redraw the benzene ring, and I'm going to put the nitronium ion right here next to it. And I'll put the hydrogen sulfate counter ion here as well, just for completeness, I guess. But same thing we did before is start an arrow at one of the double bonds in the ring. I keep picking on this one in the upper right-hand corner, but there's really nothing special about that one. I'm just doing it for consistency. But you could use any of them, and they're all equally reactive. They're all exactly the same in this molecule. So start an arrow there and show it going to the nitrogen. So that's saying make a new bond between this carbon and that nitrogen, but since nitrogen already has 4 bonds and can make at most 4, we have to lose a pair of electrons, and what you do is take a pair out of one of the nitrogen-oxygen double bonds and give them to that oxygen. And that gives a non-aromatic intermediate that looks like this. It has the nitro group installed. Just for reference, I'm going to draw in all the lone pairs that are there on the nitro oxygens in the molecule. That ring, that carbon of the ring, has a positive charge. Remember, there's a hydrogen there that's not being shown just because this is a skeletal structure, but there's definitely a positive charge there. So we've got, a conjugated non-aromatic intermediate. There are resonance structures that help stabilize this, but it has this sp3 hybridized atom that makes it no longer fully conjugated, so it's not aromatic, it's just non-aromatic. Okay, so there's that. That's the non-aromatic intermediate. And then there was a water that's left over from the formation of the active electrophile, and I'm going to use that in the next step. So step 3 is weak base deprotonates that intermediate that we made in this previous step. And I think I'm going to draw a line just to separate out these 2 steps. So I'm going to redraw that non-aromatic intermediate down here. It's got the cation on the ring in that position, resonance stabilized, delocalized onto other positions. There's a hydrogen here, and there is a nitro group here, which you can draw out as in its full Lewis structure form, or if the question permits, you can just draw NO2. That's another way of representing nitro. Now, this next step is an interesting one. What do you use as the base? There are 2 candidates for weak base in the reaction mixture. There's water, because water was formed when it left from nitric acid as a leaving group. So that's one base that you could use. The other base that you could use would be the hydrogen sulfate anion that came from sulfuric acid donating a proton to nitric acid. And depending on what example you're looking at, you might see one or the other used. Let me tell you my opinion about it. It's that water is a stronger base. So if you've got the choice, water is a better choice to use than hydrogen sulfate. Hydrogen sulfate is weaker. Water is a weaker base. This is a stronger base. So use that lone pair to deprotonate the intermediate. However, if you were to use this one, I'd still be okay with that. I mean, it's basically a counting of species. Either way, you'll get the product. This is the preferred answer, but the other one's okay too. And let me show you what then you get. So you get nitrobenzene, and then you get H3O plus, and you get hydrogen sulfate, which is that species. Now, is this a strong enough acid to keep the reaction going? That's a good question. I kind of think this probably isn't strong enough to this isn't really strong enough to protonate nitric acid. So the sulfuric acid probably isn't a catalyst in this reaction after all. It probably is actually a reagent that you have to use, because to get another molecule of nitric acid protonated, you're going to need a stronger acid than this. So people would add excess of both, basically, to get this reaction to go. But those are kind of minor points. We have nitrobenzene. That's the big exciting point. So nitro group is really useful because you can convert it into other nitrogen-containing things. We're going to learn out later you can make it into an amine, and then that amine can be made into lots of other things. And so it's a useful way of functionalizing a benzene ring, putting a useful functional group on it. All right, any questions about this one? Okay, well, let's move on and talk about number 3 then. Reaction number 3 in the list of 5 reactions. So we looked at nitration recently. Now we're going to look at sulfonation. So sulfonation looks like this. If you start with an aromatic ring and you put in a reagent known as fuming sulfuric acid, and if that sounds crazy, it is. Sulfuric acid is a really powerful reagent, but this is like sulfuric acid that's had water removed from it. It's dehydrated sulfuric acid, and the reason it fumes is that it reacts with the moisture in the air. It's powerful stuff, and it is definitely going to do a reaction with this ring, and the reaction that it does is it puts a sulfonic acid group on the ring. So sulfonic acid looks like this. It's a really strong acid. You'll see the family resemblance to sulfuric acid. If you look at this and then you just look over or look at the last mechanism where we use sulfuric acid, it's very similar to that. So this is called sulfonation. And the mechanism starts with forming the active electrophile. Formation of active electrophile. And it's a lot simpler mechanistically than the formation of the nitronium ion. It's pretty simple. Here's how it works. So if you've got the 2 things that I mentioned are in there, sulfuric acid, SO3. This is one of the Lewis structures of SO3. And then I'm going to draw sulfuric acid next to it over here. Sulfuric acid is a really strong acid. This is one I wouldn't want to get on my skin. I'll leave the lone pairs out of the sulfuric acid. Really strong acid, what it does is protonates things. It protonates pretty much everything it sees. If there's a lone pair, it'll put a proton on it. Even a pi bond, it'll put a proton on it. That's what it does. It protonates things. And so this thing has got lone pairs on oxygens. Those are good targets to put a proton onto. So a lone pair on one of the oxygens goes and grabs an H off sulfuric acid, and that gives this species which is an activated form of SO3. It's got a proton on it, so it's more electrophilic than it was before. It's got a formal positive charge now, and it really is going to be an attractive target for any electron-rich species, like the aromatic ring that has that big pi cloud in it. There is also, if you want to think about this, a resonance structure of this. So I'm going to show a resonance structure of this activated intermediate. By the way, there's an HSO4 minus counterion here. I'll just put that in for completeness. And what you get then is an intermediate that looks like this. It's got this resonance structure, and this is one that looks an awful lot like the sulfonic acid. It's got a sulfur that's positively charged. All that has to happen is the ring has to just go attack it and make a bond to it. And so that's what's going to happen in the next steps. So that's the active electrophile in the formation of this, or in the sulfonation reaction. All right, let's move over here, talk about step 2. I will erase the particulars, but I'm going to leave these headers because they're the same. We've got pi electrons of the ring attack the electrophile. So I'm going to draw the ring. I'll redraw the electrophile over here, and we'll get some arrows moving. I'm just going to rotate the electrophile a little bit to put it in a position that makes it look like the sulfonic acid a little more. So this is just a rotated version of what I had on the previous board. So ring electrons are attracted to the strongly partially positive sulfur and start an arrow at one of the double bonds in the ring and show it going and making a bond to sulfur. And that gives a non-aromatic intermediate that looks like this, where there is now a sulfonic acid group that has become attached to the ring. That was the really big point of this, is to put a sulfonic acid group on, and this step does it. Generates a non-aromatic intermediate that's resonance stabilized. And then a weak base has to come by and pluck off a proton. And in this case, I'll just draw in, what we have. The other thing that's in here is hydrogen sulfate. So in the next step, we're going to have to come up with a weak base to pluck this proton off. The best weak base we have around is actually this one. It's the only weak base we have around. So let's go draw that next step down here. So step 3 is weak base deprotonates the intermediate. And this is truly a very weak base, but it can grab its proton back. So I'm just recopying the intermediate from the product of the last reaction, and I'm going to redraw the hydrogen sulfate as well. I'm going to put that molecule on the board right here, and I'm going to use that as our weak base to deprotonate this non-aromatic intermediate. So remember, when you're doing this step 3, the thing is you got to figure out where's the weak base, and that's where you want to start your arrow. And then you want to go to the proton that's on the sp3 hybridized carbon. When people make errors on these mechanisms, it's usually they start the base outright, but they get the wrong proton somehow. But just remember, we want to get rid of that one so that we can have an aromatic ring again. That's what makes this reaction go. It's the forming this really stable product that's got aromaticity and special stability from an intermediate that doesn't. And what this reaction did was to produce the product, and it regenerated the catalyst. So in this reaction, sulfuric acid does serve as a catalyst. You get it back in the end. So you need a little bit of sulfuric acid and then a stoichiometric 1 equivalent of SO3. Okay, well that's those 3 reactions. I think that's enough for today, even though we're done like a minute early. When we come back next, I'm gonna let you out 1 minute early. When we come back next time, we're gonna talk about Friedel-Crafts reactions, which are really interesting, and they've got a little bit more depth. This first part of the chapter is a little bit tedious because it's reaction, 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 boom, boom, boom. But we're gonna start talking about strategy pretty soon, and it'll get a lot more interesting. So, but we gotta lay down some basics. So I will see you next time.